Hello, my name is Eber Barbero, and today I want to talk about backlink mode interaction in pultruded composite columns. So, by the end of the presentation, I want to reach the conclusion that the interaction constant in the design equation, which I will show you, can be found by FES simulation plus manufacturer provided data for crudeness and twist of the product, thus reducing the need for testing. So pultruded structural shapes are similar to steel shapes, but made out of fiberglass reinforced polymers. And they are used for a variety of applications for a variety of advantages they have over competing materials. And here we have two applications. On the top, we see the bridge at Kolding in Denmark, and where the corrosion resistance and the ability to assemble this bridge in 3 nights it took to assemble the bridge. That's one because of the lightweight is one of the advantages. And at the bottom we see an airport blast deflector. That's what keeps the noise from the aircraft on the tarmac away from the roads. This is in Pittsburgh, PA, from Liberty Pultrusions, and as you can see, this structure is made out of FRP, fiber reinforced plastic pultruded shapes. And the reason why this is done is because of easy assembly, but mostly because of corrosion. This is resistant, totally resistant to corrosion, so there is no maintenance, and it will last a long time. And as you can see, these two structures and many others are subject to high loads, very variable loads sometimes. And then if the load is in compression, then these shapes, these columns act as a column, and they have to be designed accordingly, and that's why we want to talk about it. So here you see on the left what we will call a short specimen of a wide flange I-beam. The wide flange I-beam has these flanges, and when you apply the load vertically with this testing machine, the column will buckle in what we call a local buckling mode. In the aerospace industry, they will call it crippling, where some portions of a cross-section buckle, as you can clearly see here with a sinusoidal shape, but overall the length of the column remains straight, and this is what we call a local buckling load. The local buckling load can be predicted accurately, or testing can be done to obtain it. And it is pretty much independent of the length or properly the slenderness of the column within some range. We're going to talk about that. And on the other hand, if the column is long or properly speaking slender, then when you apply the load, then the column will buckle in a traditional Euler buckling mode, which you studied in mechanics of material courses. And there is the Euler formula to predict this, and the Euler formula is good to predict that. So if the column is really stubby or not slender, short, then we can predict the local buckling load confidently. And if the column is quite long or slender, then we can predict also the buckling load, Euler buckling load. But if it is not too long and not too short, then we have problems, and that's what we're going to talk about today. So now we go to this old plot. It comes from one of my papers that I published in the year 2000. And so here we have on the vertical axis, we have the normalized column load. K sub I is PC over PL. PL is the local buckling, L for L, for local. Local buckling load, which, as I mentioned, is practically constant over a certain range of slenderness. And you see here it is normalized, so that it is equal to 1. So the actual buckling load should be 1, all right? But you can already see that the experimental data goes all over the place when it's very short, and in general it goes below when it is not so short or not so slender. This is denoted here as isolated local mode, because that will be the mode that you saw on the picture before, which is this lonely mode, which is local. But now here on the bottom, we have the universal slenderness lambda. Now the universal slenderness lambda is defined in this paper in 2000 And it is not the slenderness that you find in a mechanics of material book, because that formula is for steel. And that formula should not be used for pultruded or any type of composite materials. And the reason is that in steel, the interaction between modes occurs between buckling and plasticity. But pultruded columns and composite do not have plasticity, because the behavior is dominated by the fibers, which are totally elastic. So you won't have plasticity. Interaction occurs between two buckling modes. So the phenomenon physically is different. The definition of the slenderness should be different. On top of that, this slenderness lambda is conveniently defined in such a way that slenderness 1 indicates the critical length. And the critical length is where the prediction for the buckling, local buckling load coincides with the prediction for the Euler mode. All right, this is the curve for the traditional formula from Mechanics of Materials book. And so at this point, the two formulas predict the same value. This point is a point of maximum interaction, and that coincides with lambda equal to 1. So when you calculate this lambda, universal slenderness, then anything less than 1, you know, is local. Anything above 1, you know, it's Euler. And you can clearly say something is small, very long, like or very slender, 1.5 or more, or very, very short, very stubby, 0.5 or less, something like that. All right, so it's clear to use this value. Now, this value can be either measured from experiments, or it can be predicted by formulas or finite element analysis, and you are very confident about this value, and it usually is what controls the design. Then we have this formula. This formula also is very good to predict the buckling load when the column is very slender. The experimental data agree with the formula very well. Okay, and it's very simple formula. But we see that if the column is not so slender, all right, and it is not so stubby, we have this area, and this is the area of interaction where the experimental data, which also obtained by these people here, shows that the actual load of the column is less than what the formula predicts. So the designer will be concerned about this, because you know, you have to design for safety, and if you think that the load is this, but actually the column fails here, you're in trouble. So in order to do that, the designer will use an interaction equation, and here is the design equation 2.4 from the 2000 year paper, with an interacting coefficient of 0.65. And part of the objective of this presentation is to show you where we're going to get this interacting coefficient. But anyway, if you have the interacting coefficient, instead of using this curve and this curve, then you're going to use only this curve, and you base the design on that. Of course, you put safety factor or load and resistance factors on that as well. Okay, now the next thing I want to talk about before I move on is that why are we so interested about this region, critical region? And that is because the local buckling load PL is the maximum load that you can attain practically with a column that you pay good money for. If you make your design with a longer lambda more than 1, then the Euler equation will dominate, and that means that you see the Euler load drops fast with the slenderness. So a little bit longer that you make, a little bit slender column, then you lose effectively a lot of load capacity. So the designers will stay away from this curve and will always want to work in this region. All right. Now, also the designers don't want to go too short, because if you go too short, then access to the structures for maintenance, for example, let's see here, if you make all these columns very, very short, then you cannot get under here, and it's difficult to clean, difficult to maintain. All right. Also, you could make the column effectively short by bracing, but bracing costs money, so you don't want to do that either. So all the design will be pushed to be close to this region here, where you're not caught by the Euler, because that reduces too much the load capacity, but you are in this region. But this region, unfortunately, has interactions, so we have to learn how to deal with it. Okay, so now we're going to do simulation. In year 2000, I did experiments, and those are reported in the literature, but now I'm going to base this presentation on simulation. And one very important thing is that I have to mention is when you do simulation of composite material, you have to be careful assigning the material orientations in your model. And that is because composite materials have different properties along different directions. So normally we call one the direction along the length of the fibers or the axis of pultrusion, and you have to go into the model. In this case, I'm assigning the material orientation to the 4 flanges, these 2 flanges on top, these 2 flanges on bottom, and you see that I carefully put one along the direction of the flange everywhere, so I know that the property 1 is aligned where it belongs. And on the web, you see I put the 1 also along the length, and the 2 like this, so that the material properties are assigned correctly. If you don't do that, then the results will be garbage. And if you need more details about this, then you could look at this book where I explain all of that. So now we see the result of the simulation, and we see the result of the simulation again for a short or not slender column, local mode, and then on the right we have Euler mode, which is for a slender column. Of course, you've seen this picture before. If the column is slender and you put the load, all that will happen is that the cross section, the beam will deform like with a sinusoidal shape, but the cross sectional beam will not deform. But if you do a not slender, a short column, then it will not deflect laterally. You see, it didn't deflect laterally. Laterally will be this direction X. But you get this waviness, which you have seen already in the experiment. Here are the same waves. Okay, so and now, unlike the experiments where we have the same waves all along, you see here that the waves die down, and that is because the particular boundary condition that I impose here with the simulation, you have more flexibility to include different type of boundary conditions, and this is called wave modulation, and it is explained in one of my textbooks. But basically, if it is short or not slender, then we have local mode, but no lateral global mode, and if it is slender, we have lateral global mode, but no local mode. All right, and this is when it is really short or really long, or really not slender and very slender. Okay, so now we complicate the things in this graph, so I have to take time. So in these graphs, on the horizontal axis, I plot the stroke. The stroke of the machine is the deflection of the machine. When the machine pushes from the top, this will shrink this way, and that is the stroke. Same here, when it pushes, it will shrink this way, and that is the stroke. And in this case, when it pushes this way, and then we have some displacement. So that displacement is common for all 3 cases, and it is illustrated here. And in the vertical axis, I put the normalized compression load, and it's normalized by the bifurcation or buckling load of the column acting with a single mode, because that load can be calculated either as PL, local, or P Euler with the Euler formula, and it's easy to calculate. So I can normalize by those values, and I can put different slenderness of columns in the same plot. So then let's look at what happened. If I have a column with lambda, this is the slenderness, 0.707, that is a short stubby column, not slender, and that is denoted in green. And when we push, remember the stroke is we push, we go linear all the way here, and at this point there is a change in the slope, which indicates that there is a local buckling. And this is the local buckling that you see right here in this picture. When this happens, then the stiffness of the column reduces, and then we go on this green line rather than keep on going on the dashed line. All right. So from a point of view of design, this behavior is good, because if you design with a bifurcation load, which is here, 1, all right, and there is an overload, or the column is slightly damaged, well, all that can happen is that you go in this region where the column can take even more load. So in a way, it's kind of safe. If you use proper resistance factor and load factor or safety factor, then you're likely to be okay. But not for long. As this plot shows, we go on this stiffening. It's called a stiffening curve. It's called a stiffening because at least it's more than indifferent. It's something going up, not as much as originally, but something going up. but eventually it's going to catch the interaction and it's going to interact. And when it interacts, things get ugly because the load drops suddenly, and it may drop a lot. All right. So that's for a short column. Now let's go to a slender column. The slender column is black, and it has a slenderness 1.4. Remember, that's quite slender. And so it's like the picture here in black. All right. So in black, again, we push, and we get the load, the load corresponding to how much we push, until we get this Euler mode of buckling at this point, and this is the Euler mode of buckling. And the way the column behaves after buckling happens is in a way that is called indifferent. Indifferent means it doesn't go up and it doesn't go down. At least it's constant. And from a design point of view, this is not bad because, okay, if there is an overload or some slight damage to the material, then, or something happens, then at least for a while you can push more with the stroke, and the load at least it keeps constant. So if you take this value of load and you apply a good safety factor on it, then you're likely to be okay. But eventually interaction will catch up, and then you're going to have a problem. All right, so we have to study this. Now the worst happens at the slenderness that the designer will want to use, which is lambda 1, because remember I explained for lambda 1 I have the longest column that is not affected by a reduction of load, significant reduction of load due to Euler. So for lambda 1 we have the red curve, and so we push and we go up in the here like this, and very close to 1 we have a buckling. But when we have this buckling is the two modes interacting, and the load drops very drastically, and it drops a lot. And this we can see here in red in this picture. All right, so in this picture we see that an Euler mode has developed. I hope you can see the Euler mode clearly, because in this direction X, this direction like that, lateral, you can see from the undeformed to the deformed that it moves a lot. And that is an Euler mode similar to this mode here in black. Same thing as this mode on black. But unlike this one also has local mode, which I hope you can see. I'm sure you can see. The local mode is there. So both modes are taking place. And when these both modes take place, which all happen this here at this point, the load capacity of the column will drop a lot with respect to 1. And 1 is probably what you use for the design. So we got to do something about it. Now, one more note is that the imperfection amplitude I use here is 0.01 millimeters, and I apply only to the flange in the shape of mode 2, which mode 2 happens to be the local, okay, for this column. So that means I'm applying basically nothing, right? This is 10 microns. Real pultruded shapes have much more imperfection than that. And I apply so little to emphasize the different behavior and be able to make this plot in such a striking way, all right? So, okay, so now to emphasize more what's going on, I'm going to show you two movies. So I'm going to show you this movie, which is the simulation movie, where we have the same thing as in the previous slide, right here, this one. And then we go here, and then we have this movie, and we play this movie. Now, you're going to see that as soon as I apply the load, right here, very few frames, the column tilts. So I'm going to stop to talk about it. So the column tilts. It tilts because it wants to tilt. I didn't put tilting on the imperfection. The imperfection was in the form of mode local. So it was wavy, and it was 10 microns, which is nothing. But that was all it requires to do something to the column. And the column chooses to tilt. Now, once it tilts, it loses bending and stiffness, and an Euler mode will kick in. So we go here, and we continue. And you see, it tilts, and then I start to separate here from the undeformed. I left the undeformed there so you can see. So I start to separate, and that's the Euler mode. Now, when the Euler mode starts to happen, then the local mode is magnified, severely magnified over here, and that is buckling mode interaction. All right, and that's what is going to control what is the load capacity of the column for a slenderness more or less close to 1. All right, between 0.7 and 1.4 in that region. And you can see the Euler mode keeps on going. The local mode becomes worse and worse, and the load capacity of the column goes down. It doesn't go up. It doesn't stay constant. It goes down. All right. Okay, so now this movie is done with a simulation, and okay, but some people may say, well, okay, but this is just a computer program. So what I'm going to do is show you a movie that was made in year 2000, and then, or earlier than that, which is a movie of a real test. So here we have a wide flange column, same as the one in the simulation. It's not so clear to see because there is this frame with a glass, and the glass has very tiny, very thin lines, fringe, to create a fringe pattern so that we can see the deformation. Now you don't see that because of the light, but they're there. And to see the fringes, you're not going to see the fringes either because you have to see through a camera that is mounted on the top and use a special light. So, and the Euler mode is recorded with this LVDT. So if the column tries to move laterally, which is going to move that way, then this is going to record it. So I'm going to play the movie and you can see what happens. Right? At the beginning, nothing happens, but we are applying the law from this end. All right, we're pushing on this end. All right, and it looks like the top flange, it is the top flange, and nothing happens. All right, and so I put this to, okay, there you go. So you see now that you can start seeing the local mode a little bit right here with some effort. You can see it. And the Euler mode is difficult to see because you will have to measure this distance with your eyes. But the instrumentation is measuring, so don't worry about it. But now you can clearly see there is a local mode. They start to develop exactly like in the simulation. And here develop exactly, you know, the waviness. And this waviness is going to combine with this Euler mode, which is hard to keep track of because that will be this distance over here. And now it magnifies on one side, just like in the simulation. All right. And then, of course, it's catastrophic, and we broke the column. All right. So, okay. So now, all right, that we have seen the movies, we can use simulation to get more insight into this problem. As you remember, the first plot I produced with an imperfection E 0.01 millimeter, which is nothing. And with that, I was able to get the column to reach almost the local backplane bifurcation load, not quite. And then once that happens, then it has this sharp drop, which is the mode interaction, the effect of mode interaction. But in reality, the imperfections will be larger. So now I can run with an imperfection of half a thickness. The thickness is 6.35, so this is half the thickness of the flange in black. And you see when you do that, then I don't get that high. I get only here, which is 20% less than the load, the backplane load that I would use for the design if I didn't know better. So, but now I know better. If there are imperfections, I have to account for a sharp drop. This 20% is gone with this imperfection. And if the imperfection is 635, which means the thickness of the flange, then is the green curve, and with the green curve, I lost 30% of the load capacity of the column. And if the imperfection is huge, like 19.5, then there's a purple line, which it appears it doesn't have a peak, but it does. This is a peak. And with that, I lost almost 50% of the load capacity of the column. And so one thing I can do now is I can join with this blue line all the peaks, and this is called the imperfection sensitivity curve because it tells me how much load I lose as a function of the imperfection. But in this plot, it doesn't look really nice because here I don't have imperfection, I have a stroke. So I can make another plot, and this is the same thing, same data, peak load reduction from 1, go down in terms of imperfection amplitude. So now here you can appreciate that if you buy a expensive high quality column, which implies that it has low imperfections, then you may lose only 20% of the load capacity. And to lose less than that, you're going to have a perfect column, which you cannot buy. So this region will be almost impractical, all right, or difficult to get. All right, and if you buy a not so good lower quality column, then your imperfection is likely to be higher, and then you are going to lose more. Okay, all right, we're going to talk about how to measure the imperfection, where to get the imperfection. So now we have to go. Well, now we know all that. We have to go back to this old plot that has all the curves and the experimental data on it. And so in order to get this design equation. All right, I put the design equation right here in this place. So the design equation says that it's very simple. The design equation says that the actual column load P sub C, this is what I can expect to have. All right, it can be found as K sub I times PL, and PL is the local backlink load, which as I said, you can use formulas, you can use test data, or you can do finite element simulation, very simple. Backlink analysis called bifurcation analysis is very simple. So the design equation is super easy because you just multiply by a factor. Now you gotta get this factor. Now to get this factor, first you gotta calculate the universal slenderness that I promised before that it was an easy equation. Okay, here it is. The universal slenderness is equal to K. K is to take into account the end condition of the column. Like if it's pin-pin, simply supported at both ends, K equal to 1. And these values of K you can find in textbooks because it's very common in the literature. The length of the column is your design length, pi. Then PL, like you can get PL from experiments, finite element analysis simulation, or formulas. And EI, everybody knows, modulo elasticity multiplied by second moment of area. All right, so the slenderness is to calculate the universal slenderness. And then the actual column backlink that you can expect is K sub I times PL. Now we gotta calculate this K sub I. Okay, K sub I is K sub lambda. Oh my gosh, he introduced another K. But let's see what K sub lambda is. K sub lambda is 1 plus 1 over lambda squared. No problem, we got lambda. Divided by 2C, or what is the C? C is the interaction constant, which according to this graph is 0.65, but careful because 0.65 is from experiments that were done in year 2000 with columns produced, one particular type of column produced in year 1998, so it may not apply to your columns today. So, but you have to have this value. You got this value, then no problem, you can calculate K sub lambda, then put K sub lambda here, there is C again, lambda again, no problem. You do this, you have K sub I, that's it, you have your design equation. So by now, the only problem is where are we gonna get C? All right, and that's what we have to talk about. All right, so now to show you the power of the simulation, then I can do many imperfections, E over T, which I put on this axis. And I can do many slenderness from short to long columns, or not slender to slender columns, really. All right, over here and plot this and normalize so that everything should go to 1. Okay, and so if you see it here, the lower curve is gray, and that corresponds to lambda equal to 1 because that's critical length, and the critical length is the one that has more interaction. So I expect to have 1, but as soon as I have any imperfection, this is going to drop, and it drops fast. All right, it drops very fast. And if I go to shorter, not so slender columns, I go to lambda 0.9, which is orange, you know, the effect is not so high. It's still high, but not so high. And if I go to 0.8, which is even shorter, the effect is high, but not so high. So I got less effect when I go shorter. And when I go longer, the same. If I go longer or more slender, I go to 1.1, from 1 to 1.1, the effect is a lot less. And 1.2 is even less, and 1.3 is even less. But there is always an effect, all right? You see, no matter what you do, what lambda you use, what imperfection you use, you're gonna have an effect, all right? So now, armed with all this data, all this dot, what I can do is I can go to this plot, also from the paper in year 2000, and I'm sorry, it's a complicated plot, but this is a Southwell interaction plot. And here what we do is we create these two variables Q and S. Q is the actual load that you either test or calculate with simulation, divided by PL, which, you know, we have. This value we can calculate, we have. And here S is the actual load again, divided by PE, which will be the Euler backlink load, which we can calculate with a formula from any book, all right? And we plot all the data. In this case, this data is experimental. We have into this plot, and we have one dot for each imperfection, E over T, and each slenderness lambda. All right? So whether it's experiments or simulation, then what I can do is I put all these imperfections, yes, and then I can fit a curve. The curve is given by this equation, Q plus S, 1 plus CQS, and here's the famous C. All right? But Q and S, I know because I have the data to do Q and S. So I can calculate C, yes? So I can calculate C for each simulation point or for each experimental data that I have. All right, and then what I can do is average all the C's for a certain group of columns. All right, and then in the next slide, presented this way: the interaction constant C, which is obtained as the mean value of all the C's for this imperfection. All right. Now for this imperfection, I have several lambdas. All right, and I do this because I don't know what lambda you are going to use in the design. Yes. So only thing I can say is that the imperfection is 0.5, and I don't care what lambda you use, what length of column you use. I will put them all together into this point. And if the imperfection is 1, I put all the lambdas here, all the lengths here, and all the columns that you might possibly want to use, I put them together in this point with imperfection E over T, because what I want is to catch the effect of imperfection, all right, and apply to all the lengths. And of course, once I have the mean, I can draw these lines fit with a second order polynomial, which is here, and this I copy here in this bottom line, and there's your C. C for this particular beam, which is WF 6x6x38, production year 98, all right, for that particular, then C is 1 minus 0.177 E over T, this is imperfection divided by the thickness of the flange, minus 0.0538 E over T squared, all right, and it fits very nicely. And the other equations I already used, I already explained. And here you have C. Of course, if you know how to calculate C, then you got everything. Okay. So now a couple more things. First, we could take these values of P sub C, which we get with the design equation, which is this, and then apply a safety factor or a low resistance factor to it. But maybe we want to do reliability, and if we want to do reliability, we need either basis values or at least confidence. And here I plotted the 90% confidence value. How do I do that? I use the standard deviation, which I'm not showing. Every time I compute a mean, I have a standard deviation. I use that to calculate the confidence, and then I plot the confidence. And with that, you can do reliability analysis. All right, that's one thing. The other thing is that I said that, okay, the design equation is PC, Ki, PL. The only thing I really need for Ki is C. Oh, now I got the C. And the C is a function of E over T. T is the thickness of the flange, and E is the imperfection. Now the question is, where I'm going to get the imperfection? Okay, the manufacturer, most manufacturers at least, give you two values that you can use to calculate the imperfection. One is the crookedness, or camber, or curvature, which is illustrated here. You buy a straight, you hope the column you buy is straight, but it is not totally straight. It has a little bit of curvature. And if you know that value, then you can calculate an imperfection. And the other thing is, you think that the cross-section is perfectly aligned, there is no twist, but really there is a little bit of twist, all right? And if there is a little bit of twist, that number, the twist per unit length or something like that, will be given, hopefully, by the manufacturer, and if it's not, you demand that they give it to you. And with that, you can calculate an imperfection. Now, there is a question about what imperfection should I consider? This one, the sum of these two, or what? Early research, that's going on right now, suggests that it doesn't matter, okay? But I'm not going to swear it doesn't matter because I don't have all the facts. But in principle, it appears that whether you put this imperfection or that, the interaction will take place, and it will take you to more or less the same place anywhere, same load reduction. All that really matters is the amplitude of the imperfection. But I cannot swear by that because I got to do more research to find out if that applies in general and with confidence and all that jazz, okay? So up to this point, we have everything because we get these things from the manufacturer, the imperfections. Then with that, we calculate our imperfection. With the imperfection, we have C. Once we have C, we can calculate the actual load capacity of the column, and then we apply safety factor or load factor, resistance factor to that, and then pretty much we're done. All right. Now, if you want to dig into all these things, then you can read one of my books, which are here on the screen. And with that, I thank you very much for your attention. Thanks a lot.